Let us consider the following example. Say we have two capacitors, C1 and C2 in a series configuration that are connected to a switch that is initially open. At time t is equal to 0, the switch closes, which then allows current to flow from the capacitors through a resistor. If a resistor has a value of 250 kiloohms, the capacitance of our first capacitor is 5 microfarads, that of our second is 20 microfarads, and the initial voltage potential across our first capacitor is minus 4 volts, and the voltage potential across our second capacitor is 24 volts. We want to determine the voltage potentials across our capacitor as a function of time, the voltage potential across our resistor as a function of time, as well as the current as a function of time for all time t is greater than or equal to 0. To begin, we first recognize that our two capacitors are in series, and thus our capacitance adds like resistors in a parallel configuration. That is, our equivalent capacitance of C1 and C2 would be equal to C1 times C2 over C1 plus C2. Thus our equivalent capacitance is 4 microfarads. The total voltage potential across our equivalent capacitance is equal to V1 plus V2, or 20 volts. Thus our two capacitors in series are acting like a battery with an initial voltage potential of 20 volts. Thus, with an expression for equivalent capacitance, we can re-express our circuit as follows, where we have an equivalent capacitance with initial voltage potential connected to a switch, which closes at the time t is equal to 0, which then allows our capacitor to discharge, providing current to our resistor. For us to determine V of t, our voltage potential across a resistor, we first have to determine I of t via Ohm's law, and then we're going to sub this back in to determine V1 and V2. To determine our voltage potential across a resistor, we will consult our equation describing the behavior of an RC circuit. Our voltage as a function of time is equal to our source voltage, VOC, plus our initial voltage, V0, minus our source voltage, VOC, that quantity times e to minus t per tau. Starting with our time constant, tau is equal to RT times C, where RT is the resistance of our resistor, 250 kiloohms, and C is the capacitance of our equivalent capacitor, 4 microfarads. Thus, our time constant tau is equal to 1 second. We note that VOC is equal to 0. That is, we have no source voltage. We only have initial voltage, V sub naught. Therefore, V of t is equal to 20 e to minus t. The current running through a resistor is simply found via Ohm's law. I is equal to V of t per R of t, where V of t is equal to 20 e to minus t volts, and R of t is equal to 250 kiloohms. Thus, I of t is equal to 80 e to minus t microamps. Thus, the voltage across our capacitors can be found by the equation describing the current running through our capacitor. Or if we solve for a voltage potential as a function of time across our capacitor, we have 1 per capacitance times the integral of I of t dt plus V of naught, our initial voltage potential. For our first capacitor, we recall our voltage potential is equal to minus 4 volts. Thus, our voltage potential across our first capacitor is V1 of t is equal to 1 per 5 microfarads, our capacitance of C1, times the integral from 0 to t of 80 e to minus x dx minus 4 volts. Minus 4 volts is our initial voltage across our capacitor, and we are integrating with respect to time. However, we just executed a change of variables. Thus, our voltage potential across our first capacitor is equal to 16 e to minus t minus 20 volts. As time tends to infinity, our voltage potential across our first capacitor is going to tend to minus 20 volts. For our second capacitor, we recall our initial voltage is 24 volts. Thus, our voltage potential across the capacitor as a function of time is equal to minus 1 per 20 microfarads times the integral of 0 to t 80 e to minus x dx plus 24 volts. Or the voltage potential across our second capacitor is equal to 4 e to minus t plus 20. The total voltage potential across the system is expressed as V1 plus V2. Our voltage potential across our resistor as a function of time is equal to 20 e to minus t. Our voltage potential across our first capacitor is 16 e to minus t minus 20, and our second capacitor is 4 e to minus t plus 20. Summing these two values, we'd have 20 e to minus t, which matches that voltage potential across our resistor as a function of time. Thus, as time tends to infinity, V of t is going to tend to 0 across our resistor. However, our voltage potential across our first capacitor is going to tend to minus 20 volts, and our second capacitor is going to tend to 20 volts. Graphically, we could show this as follows. V of t, the green line, is going to be our voltage potential across our resistor. It starts at 20 volts initially and tends to 0 volts as time increases. Our voltage potential V of 1 at t starts at minus 4 volts and tends to minus 20 volts, where V of 2 at t starts at 24 volts and is going to tend to 20 volts.